Part 2 pre-calculus of 4.8. So you guys got the procedure down, right? You see something like this, you automatically think to yourself, if I log both sides, I get rid of the exponent and turn it into a coefficient. So bringing the coefficient down, you get x squared minus 5. That whole thing gets multiplied by log base 10 of 3.9. On the other side of the equation, you get 2x times log of 17 now. Now I got x's on the left and x's on the right, so definitely what I want to do is convert those logs into decimals and then work out, okay, what's the x coefficient as a decimal, what's the x squared coefficient as a decimal, and then what's the constant that remains after that. So log of 3.9 times x squared. Log of 3 times negative 5. Did I say 3 time? I meant 3.9. Oh my goodness. Okay. Log of 3.9, it's going to be a decimal. 0.591. So right away, keep in mind that we've kind of compromised the integrity of the solution. Like, it's not going to be exact. If we round to the nearest thousandth, then that's going to give us errors probably to the nearest thousandth. So 5 times log of 3.9. You get this. On the other side, double log base 10 of 17. 2.461. And don't get lost in the sea of decimals that there are x's in different places. And oh my goodness, an x squared, an x, and a constant, that can only mean one thing. Quadratic formula. So move this to the left-hand side, so we put this thing in standard form. I got to subtract it. And now we have to plug each of these components into this beast right here. So it really is a pain to write these decimals out over and over and over again, but it could be worse, right? So I don't have a whole lot of room over here. I've got 2.461. Remember, it's the negative of that. It's already negative. Plus or minus the square root of b squared, that's our b term. And since you're squaring it, you can just kind of neutralize that negative. Don't even pay attention to it. Minus 4 times a. See what I mean? This is just, oh my goodness. C divided by 2 times 0.591. Maybe do a better job of showing your work than I did in this situation. I am more restricted in my space, as you see, but yeah. So up here, something that makes a little more sense would be 2.461 plus or minus. I'm just gonna type this whole string of things in my calculator as I see it. Okay, so painstakingly difficult computations, but I have a computational computer, so that's not a big deal. 2.461, now we'll do the plus first, plus that square root. Equal it out, divided by 1.182. We get approximately 9.453. On the subtraction end of things, Negative 5.289. I mean, if you really want to, you can do a quick check to see if that satisfies both of those equations. In fact, I think I can store this as x and then just type it in as is. I'm going to do a quick check. Okay, that's interesting. Equally interesting. They're both very tiny numbers. Okay. The next page is all about inequalities. Or no, it's not. Number 5 is completely different. My apologies, by the way, if there was a calculational error in there somewhere. It's kind of like a minefield when you do these problems where you just might get tripped up every once in a while with one of those lengthy decimals. All right, so if you see a square root, you got a couple different options. If I wanted to get rid of the square root, I could square both sides, right? That seems like a pretty simple option. And you got to remember your rules of exponents. A power to a power means multiply the two little exponents. So this is now 12 to the 2x, not 12 to the x squared. The root has now been neutralized. Neutralized? 3 to the 3 minus 3x. I know, that wasn't not my greatest pun. Log both sides to get rid of these and move forward as you normally would. So if I put a log to both sides, the 2x comes down, the 3 minus x comes down, and then you have logs of the two constant bases that you were working with. Now I can distribute both of these. By the way, if you want to see what this looks like by just keeping them as logs and not doing the decimal dance, here's what it looks like. So 2 times x times log of 12. Hey, you know what? This is the same as x times 2 of log 12. Right? And this is 3 log 3. And this is minus x log 3. If I wanted to, I could move the 2 now up here to the 12. Why not, right? So it's x times log of 12 squared. 12 squared is 144. Interesting. Just like this is, the 3 can move up there. Log of 3 cubed would be 27. And this one doesn't really have any interesting properties to it. Again, everything I'm doing from this step forward is just kind of like a beast treat type situation where you don't have to do it like that. You can just go back to the boring decimals. This is just a little interesting for exploration. So now, I want to get the x's on the same side. So I'm going to add this to the left-hand side. So you got log 144 plus x log 3 equals log 27. Now, I can factor out an x from these two parts. Okay? I can take the x, divide it out here, and we got that. So now, hey, you know, remember when logs had the same base on our last assignment where addition of logs of the same base can consolidate them? That works here too. So it's x times log of 144 times 3. That's 432. So x equals log base 10 of 27 divided by log base 10 of 432. Now, I don't want you guys to get the idea that you can now say this is the same as subtraction, because it's not. Subtraction of two logs goes to division, but division of two logs does not go backwards to subtraction, okay? This would be your final result, and if you wanted to figure out what the decimal was, we do have our calculator. But anyway, that was just me having some fun with the properties. 0.543. So if you've got something very, very close to 0.543 by doing it the long way, in fact, let's just do that really quick. Let's just pretend we have decimals here. Log of 12 is 1.079. So that's 1.07918 blah, blah, blah times 2. 2.158x. Over here, 3 times the log base 10 of 3 would be 1.431 minus this number in front of x. So if we add that to both sides, we get 2.635x on the left, 1.431 on the right. Divide both sides by 2.635. Wow. Same answer. I guess this is the quicker route, but this one's more fun. Okay, number 6. All right, one inequality. Just the only reason why I threw this one on the assignment was to just show you guys, to demonstrate that the properties of logs that work with equations are the same properties that work with inequalities. So if I can take the logarithm of both sides to bring down the property, I can, for equations, I can do the same thing with inequalities. So I can log the left, I can log the right, just make sure it's the same base. So log base 10 is what we're using here. Perhaps using the decimals would be a very good idea here. I think our videos, we're approaching 13 minutes, so let's just solve this thing and get on with our lives. Log base 6 of times 2 is 1.556 x plus, you know what you could do on this calculator? You could divide by 2, get your log decimal back, then times it by 7. So you don't have to keep typing in those numbers, all those logs. Well, I guess it worked on one of them, because now we're switching to a different log. All right. Log base 10 of 11 times 5. As you see, guys, I'm going a little stir crazy here, teaching to a computer screen, talking essentially to an image of myself. Strange. Yeah. And bells are ringing, but there's no students walking the hallways. All right, get x by itself, same as before. You know what? I think I'm going to add the 1.041 to both sides, and then move this x term to the right. All right, our final answer is 1.777 is greater than or equal to x. So keep in mind that this is the same thing as x is less than or equal to 1.777, which is negative infinity to 1.77-ish, and you would include whatever that exact value was. That's actually interesting. How would we write this notation if we're doing an estimation? Is there a greater than or equal to ish symbol? I don't know. That's 16 minutes, so I won't take any more of your time. Hopefully you guys find this to be educational and fun. Thanks for watching.